we're diving into catalysts, what I like to call chemistry's secret shortcuts. A lot of chemical reactions face this massive hurdle just to get going. It's like they're facing a huge uphill battle. I want you to picture this. You're trying to push a giant boulder over a mountain. Just getting it up to the peak takes a ton of effort, right? A huge push of energy. Well, chemical reactions are kind of the same. That initial energy push is called activation energy. And if there's not enough of it, a reaction can take forever or just not happen at all. So how do we solve this? How do we get that boulder over the mountain without completely exhausting ourselves? It's time to meet the catalyst. So what is a catalyst exactly? It's something that speeds up a chemical reaction. But here's the really cool part. It doesn't get used up in the process. Okay, so there are a few ground rules for being a catalyst. First, as we said, they're reusable. They don't get consumed. And a key point, they make things faster, but they don't give you more stuff at the end. They're also total specialists. One type of catalyst usually only works for one specific reaction. But the most important rule, their big secret,
They provide an alternative pathway.
so how in the world does a catalyst create this shortcut? It offers the reacting molecules a totally new and much easier path to take. Let's go back to our boulder on the mountain. Without a catalyst, you've got that long, hard, sweaty climb. But with a catalyst, you don't have to climb the mountain at all. The catalyst basically drills a tunnel straight through it. You start in the same place and you end in the same place, but the journey is so much faster and takes way, way less energy. And that's the whole game. By providing that tunnel, the catalyst lowers the activation energy. And with that energy barrier so much lower, way more molecules collide and react successfully. More successful collisions per second means a much, much faster reaction. Okay, so that's the theory, but let's talk about the real world. And these industrial workhorses are everywhere. The iron in the Haber process, it's used to make ammonia for the fertilizer that grows our food. Nickel helps turn vegetable oil into margarine. And in your car, that catalytic converter uses platinum to clean up toxic exhaust fumes before they pollute our air. So let's take a quick look at how that Haber process actually works. First, nitrogen and hydrogen molecules land and stick to the surface of the iron catalyst. Then, the iron surface works its magic, weakening their bonds, which are normally super strong. This lets the atoms rearrange into ammonia. And finally, the new ammonia molecule just floats off, leaving the iron surface wide open for the next batch. It just keeps going, over and over again. But you don't have to go to a massive factory to find these powerhouses. It's time to meet the catalysts that run your body, enzymes. So how do nature's catalysts stack up against the industrial ones? Well, they're pretty different. Industrial catalysts are usually tough, simple metals that can handle insane temperatures. Enzymes, on the other hand, are these huge, complex proteins, and they're delicate. They work perfectly at your body temperature, but if things get too hot or if the pH balance is off, they just fall apart. And the way they work is just so elegant. A specific molecule fits into a little pocket on the enzyme called the active site, kind of like a key in a lock. But then the enzyme actually shifts its shape a little to get the perfect grip, and the new products are released. This frees up the enzyme to do it all over again, sometimes millions of times a second. This is happening constantly, powering everything from you digesting your lunch to your cells making copies of your DNA. It becomes pretty clear that without catalysts, most reactions would be way too slow and need way too much energy to sustain our world.